This conference will now be recorded.
Okay. This is, and I've got a couple of opens that I'll save for our opens component. But this is roughly a rolling agenda. Anybody have any thoughts on any other agenda items we need to add? I've just closed the loop with Professor Iyer from UCLA, and I hopefully will close the loop with Professor Flynn.
Bappy, I see you're filling up October now. Should we slot in the memory discussion in there somewhere?
Well, hold that thought for the opens.
Okay.
So I've just have the speaker ideas. We don't have anybody tangible lined up, so there is one. There is an open I have. I have a chat window. Okay. Any other speaker ideas that we need to look at? Okay, in that case, I'm going to hand it over to Shahab. Shahab, you've got about, Ravi, how much time do you need, you think?
25 minutes.
Okay, so we'll save about 10 minutes for opens. So Shahab, maybe 25, 30 minutes?
Yeah, I will try to go as fast as I can.
Okay, so in that case, let me stop presenting. It's all yours.
Thank you. Can you see my screen?
Yeah.
Okay, thanks everyone. And today I think the main point is to talk about the basically IR lab and see what we are doing in the chiplet environment. I'm referring a lot to the TerraPhi. TerraPhi is our basically the name for our chiplet module. Just to make it clear, it's an optical I/O. Okay, I'm gonna start the talk with a little bit of motivation. Why do we think that we need optical I/O, and if we need optical I/O? What basically requirements are for it? Then I'm gonna deep dive a little bit on the micro ring architecture that we have. Then presented the result from the TerraPhi, and also a little bit of how we are dealing with the challenges of the chiplet ecosystem and some of the demonstration that we have done so far. I think if we look at the I/O trends and requirements, we see that actually the total power that we are dissipating on the package is actually exceed the power for the off-chip I/Os. That actually is kind of ringing a bell in what we're gonna do in the data center, how we can reduce the power for I/Os. To actually go through that scenario from electrical I/O to the optical I/O, we see that if we can move the electrical I/O inside the chip, maybe we can solve the problem of the power basically at this stage. And meanwhile, when we look at actually the power for optical I/O and others basically electrical links available, we can categorize them in the three level. One is in package, one is in onboard, and another one is offboard, which is we refer as optical modules these days. We see actually that electrical links, the SerDes one, the long reach one, at least for now, is actually got saturated to the 112 gigabit per second. And so far, we haven't seen any good proposal for 224 on the long reach. And that's going to be a limit for electrical as well, and how we can actually move from the basically solve this problem of the electrical. When we look at the trends, we see that, okay, there are a lot of good stuff in electrical, in package and onboard, and the good stuff actually in opticals, which is basically offboard. That actually makes our lab thinking, if we can actually bring this optical to the in package, then we're gonna actually get something like the 4x improvement in terms of the speed. That was basically the motivation for us. To be able to do that, to bring basically the optical I/O inside the chip as a package, we need to have a couple of things. By that is, this is actually first of all the top level stuff that we need. Our solution is that we're gonna have actually a big chip, which is gonna be in either organic package or interposer. And the host SoC is gonna be here. It could be either CPU, GPU, FPGA, ASIC, any kind of chip. And now we're going to have our chiplet, which we're going to terafy. And this chip is going to be actually enabling the optical I/O. Then the main host chip can communicate electrically to this chiplet, and then this chiplet to the outside of basically the package through the optics. And we in our solution was actually to move this the laser source outside this, then we can actually build everything in the CMOS. To be able to do that, we need a couple of basically system requirements. First of all, we need to be able to build this optical in the very, very high dense form and close in as close as possible to the circuit, or if it's possible, monolithic. And also we need to have some kind of CMOS infrastructure and I/O standard as well. And while we are doing this, we need to actually have a very reliable manufacturing process as well. If we have these three elements, then we can actually design some kind of laser source, which is actually a lot of wavelengths close by to each other to actually enable WDM links. And also we can, with basically these three requirements, we can build the chiplets in the CMOS fashion and make it integrated to the other system as well through the chiplet ecosystem. And also to be able to make it actually to the product, we need to actually have a very good high yield manufacturing and packaging for fiber attach and those kind of things that we also needed for it. One of the challenge for the optics is actually usually the optical modules are taking so much area. That's why it's pretty hard actually to make them integrated with the CMOS. Mainly because the optical module are using something that they call Mach-Zehnder modulator, but there are another solution, something that we call it micro ring, and that micro ring was actually pretty small. It's in the few tens of micrometers. Then we can actually integrate it in the CMOS fashion also if we can. That was basically the motivation and the solution that we picked to go for it. And this, if you look at this link, we have an off-chip laser, as I mentioned. This off-chip laser through a fiber is going to get coupled to the chip. In this case, I think we show the grading coupling. And then we have a waveguide or light guide here. And there is a micro modulator ring here that actually modulate the laser for us if you look at it as a transmitter. And this modulator needs to be actually get modulated by a driver, electrical driver, which is close by to it. And the output of this basically waveguide is going to be a modulated laser. The modulated laser again is going to get connected to a fiber, transmit few kilometers or few hundred meters, depends on the application, and it's going to get to the receiver chip, which is going to be again the same scenario. We're going to have a detector here again based on a ring, and then convert the basically opticals to the electrical receiver. One of the advantage that we get from the micro ring based WDM optical architecture is that these two modules itself, the ring modulator and the detector, they're gonna act as basically a MUX and DMUX for us as well. How it works is basically if I have a laser with the lambda 1 and it's coming to the system, this modulator, if it's get tuned to the lambda 1, is gonna only peak the wavelength of the lambda 1. Look at it as a frequency division multiplexing access that we do in the RF. This is quite similar to. There was a question. Yep, we can actually look at it from the RF perspective similar, but over here we are actually modulating or doing some kind of division based on a wavelength. If we're doing that, then we can easily have another lambda on the same fiber. We don't need to actually have another fiber and pass the second set of the signal or data through the lambda 2. And this is actually keep increasing. And we think we can actually do it all the way up to the 6 microrings.
Hey Shahab, are you taking questions during, or do you want them all bunched up at the end?
It's up to you. You're managing the time.
Well, that's fine. If anybody has any questions, pop in. So I don't, but
you said 6 microrings, but you wrote 64 microrings on that last one.
Yeah. This is said that for a fiber, for a single fiber, we can actually have up to the 64 micro rings, which is the 64 lambdas in one single fiber.
Okay, so 64, not 6. Okay, thanks.
This is basically a larger ecosystem that you can see is a system of the basically optical link. What we're gonna have again, I'm gonna mention we're gonna have an off-chip laser. One of the two, there is two advantage for putting the laser offsite. First of all, the laser is very sensitive to the temperature. You can actually have it as far as possible from the basically the hot electronics that you have. It's increased the reliability and lifetime of the laser. And number two is usually generating laser in CMOS. It's impossible because of the nature of the CMOS. You need some kind of 3-5 material. But then if we push this problem away and get the benefit of the thermal, then we can actually implement everything in the CMOS and make it basically a monolithic architecture. In this presentation, we do have an off-chip laser here. For example, right now we picked actually 5 lambda. 5 lambda is coming here. It's again a one single laser cable with the 5 different lambdas on it. And each of this modulator, they're gonna actually modulate specific lambda, lambda 1 to lambda 5, and then transmit it over again a single fiber. And the single fiber is coming here, and the receiver, because it acts like actually filter for us too, is gonna only pick the lambda 5 all the way to lambda 1, and then we're gonna have it to the CDR for electrical communication. Let's see how we build basically this system. This is our one of the chips that we built. If you look at the left side, for sure, because we are in the chiplet domain, I'm sure all of you guys who are on the call, we are familiar with the chiplet ecosystem. We need to have a kind of communication channel to the main SoC. We picked AIB, and if you look at this chip, it's a 8 by almost 9 by 5.5 millimeters. The good chunk of it actually is dedicated to the AIB. We have a 960 gigabit per second bandwidth of the AIB, 24 channels. And through the right side, this is actually where the large blue one is where the optical is gonna get connected. The fiber optic physically is gonna get mounted here. And then we have a 10 bank of RX and TX combined, which are the main converter of the optical to electrical link, if you want to call it. And for sure, between the AIB and the main link that we have, we need to have a kind of glue logic here or pipe adapter, different name. People put a different name on it. Advantage that we get through this architecture is by we can actually work it up to the basically 256 gigabit per second per macro, which is in total chip, because we are talking about the 10 macro, we can get it to the 2.56 terabit per second chip. And we are using NRZ modulation, then we don't need any FEC, and therefore the latency is pretty low. From what we measured from the input to the AIB, all the way going to the optics, feedback again to the transmit to the optics, receive it to the same chip, pass to the AIB. Again, at the end of the AIB, we are thinking something less than 10 nanoseconds, and plus the basically how many meters you go through the optic, which is 5 nanosecond per meter for optics. But if it's a short distance, we can ignore that.
Quick question. So obviously, you know, really we're in transceiver land, so to speak, as opposed to parallel bus land, you know, and normally QSFP optical modules are converting transceivers from electrical to optical. What made you choose the bunch of wires approach, i.e. specifically AIB here, rather than just the extremely short reach? So you'd have, you know, so basically you'd have, I guess, 100 gig or something like that, transceivers on the silicon, taking up far less area, being able to use organic substrates. You know, why choose AIB and not an extremely short reach channel?
I have 2-3 slides on that one. I would go more details, but I think if you ask different people in the company, that you have a different view. But I'm gonna say, first of all, the customer is important. You have to see what it's a chiplet. I think this is one of the challenge of the business model for the chiplet, and which basically parallel bus you're gonna pick. to communicate to the main chip. And I think that sometimes get forced by a customer as well.
Who's the customer in this? You mean the customer or the processor supplier?
Usually your customer is the processor supplier. I mean, this is
Yeah,
you are selling your chiplet to a main guy, basically. Let's put it this way. It's either
a customer's a data center, really, and a systems level person is buying the packaged part, and they're the real customer, and they probably don't care what that bus is, to be honest. But anyway,
I think it depends who from which angle you're looking at it. But if you, for example, targeting in a specific, for example, in our case, our customer is FPGA of the Intel, and then they're gonna actually make the FPGA with the optical communication. Then our customer becomes basically Intel, and they prefer AIB. For example, if you go to the Cisco and maybe they prefer XSR or something else. I mean, when I say customer, I think the first level of the customer, not the end customer.
It's your internal customer, yeah. No, that makes sense. All right, thanks.
Yeah. But that was a pretty valid question. I think this is the main challenging question from any chiplet company, that at the beginning, maybe even if you don't have a customer, you have to pick one of these parallel lines or serial lines. But I have a slide. I think there are a couple of more reasons for it. It's not just the customer. We believe parallel lines, Bo wasn't available when we start this. We think parallel bus like AIB and others are a little bit easier to implement compared to the XSR, and actually they are taking maybe less power as well. The reach that we are basically getting from this fiber optic architecture, we can actually go all the way to 2 kilometers, and our power estimation is, including AIB, is something like 5 picojoule per bit. And the roadmap is actually we can increase this one to the 25 terabit per second per chip as well. To be able to do this, basically the entire thing that I propose, we need a lot of stuff that needs to be able to basically build in the CMOS ecosystem, because usually in CMOS you don't have that much of the optics. First, we need to actually build the silicon waveguide. You can actually pass the electronics to it. You need to create the micro rings, modulator, and detectors. And also you need to find a mechanism to couple basically the fiber optic to the chips. That was basically the 3 area that we worked on it when we were using actually the CMOS process. And we finally actually did it. And that was the first demonstration or first chip that we built. This is the full wafer level of the TeraPHY in the CMOS process. Each of this is small basically die. If I zoom on it to it, you're gonna see the same thing that I presented. At the left side, you're gonna see the AIB. Then we have a crossbar or glue logic. Then we're gonna have a 10 macros of the TeraPHY. And at the right over here, you can see actually how we couple the fiber array, basically. 10 fibers is gonna come. And if you look at the BOM, for sure you see the very dense one, 55 micro, which is for AIB communication, and then the larger one for the normal communication or power as we need. If I zoom into the process chip, to just one of the macros, we said that we have a 10 macro. Each macro has its own basically 8 wavelengths. For 8 wavelengths, we need to have a basically 8 RX and TX and shared clocking between them. On the top of the screen, you see the RX, bottom you're gonna see the TX, and there we have a 2 PLL to cover the range that we want, and this is a clock distribution and IQ generators. In more details, again, this is the top part of each slice. Again, remember we have 10 macros. Each macro has 8 TX and RX. In total, we have 80 TX and 80 RX. Each RX is basically TIA equalizer and other logics for the temperature control and those kind of thing. This is a clock distribution in the middle. We have a phase interpolator, IQ generator, ILO, and then at the TX part, which is at the bottom, we have a TX heater and driver and eye monitor for our internal test. But one thing that I like actually to point here, if you see these 2 small dots and 1 single dots here, these are basically the ring resonators. One of them is going to act as a modulator, and 2 of them is for the receiver. One of them act as a dummy. Then you see how optics basically is small still compared to the electronics if we move to the ring. But usually if you use the standard way of the Mach Zehnder, we are talking about actually much larger than this area. And these two red colors here are basically our optical guide. Okay, maybe that from here, I think we're gonna have answer some of your. Yes.
So in the previous picture, does that mean you have like 80 different lasers connected to one die?
Actually, we have 10 fiber cables that are coming in, and each fiber actually has 8 lambda laser. Yes, 80. I don't want to say 80 different, but there are 80 lasers, but categorized in 8 wavelengths.
I see. Okay.
Basically, we have 10 lambda 1s, 10 lambda 2s, all the way to 10 lambda 8s.
So you need one cable. Sorry, go ahead, Anu.
No, go ahead, Bapi, finish.
No, I'm done. Go ahead, please.
So those laser drivers are now off packaged, right? They're because of the heat they produce. Is that correct?
For 2 reasons. Number one, if you want to generate the laser, you cannot do it in CMOS. I think there is only one.
Oh, it's a 3.5. Okay.
Yes. And the second, I think, thing is, although we pushed it away because it was a CMOS things, but also there is a new trend that even the module guys trying to actually push it away because of the reliability.
Oh, I see.
Yes.
So, just another question on that. So each of the micro rings has got 8 lambdas, and there's 8 of them, so that's the 64. So I understand that correctly?
No, if you see there, for example, for each lambda, you need actually 1 micro ring.
Oh, right, okay.
Actually, you need 3. 2 for receiver, 1 for transmitter. One of the receivers is dummy. You can ignore it. But when I actually point to the three here, this is one pair of the TX and RX, and we have 80 of the TX and RX. Each of them, they're gonna actually have a 3 ring resonators.
80.
80, yeah. 10 macros.
Oh, so this is just one slice we're looking at, but there's.
Yeah, if I just go back, you can see.
Right. This is on one packaged FPGA, right?
Yes, and then maybe I should go reverse.
So how many cables are there coming into each chip?
Yeah, this is the 10 macros, and each macro has basically 8 wavelengths.
Right. And 1 cable.
And each macro has a 1 cable. Over here, you see the majority of the space is actually for how to couple this fiber here. And 1 fiber is gonna come here, 1 fiber is gonna come here, 1 here.
Right.
But you have a second cable for the laser itself, right? From somewhere.
You have 1 TX, 1 RX, 1 laser. You have 3 cables.
3 cables, okay.
1 TX, 1 RX, 1 laser for a complete link. But you don't need to push the laser to the RX as well. That's why you just need the laser for TX. Over here, we don't do laser forwarding, Bapi. We don't do clock forwarding. Okay, I think this slide is quite familiar for most of us who are dealing with the chiplet. I mean, we all know why chiplet is good, but just to add to it, most of the people talk to the chip when they advertise chiplet is to mix die functionality or have a memory on it, but also optics is another issue. I think if you want to actually co-package optics, then you need to have a basically a reliable solution for it as well. Back to the question that we have, why we picked that one. I think this is a very simple and abstract slide to somehow compare basically the serial link versus parallel, which you see a little bit easier if you want to implement it in parallel. First of all, package complexity is moderated and design complexity is much lower. Energy efficiency is a little bit better, and bandwidth density is still the same. That's another reason that we pick basically the parallel. For us doing the parallel, yes.
Sharp's quick question. The previous slide, there is a fairly decent price difference between one and the other, right? Going into poser is a lot more expensive than organic substrate. Does that filter into the thought process, or that was customer driven, so it didn't matter?
Actually, I was thinking it the other way. I don't know, maybe I'm totally wrong. Maybe I have to refresh my basically thought. I thought organic substrate yeah, you're right. Interposers are expensive. You're right. Sorry, I got it confused. Yeah, this silicon interposer are a little bit more expensive, and I agree with you. But again, you have to see who is your customer. And
right. Well, the other thing is on the bandwidth density per millimeter, you've got a lot more depth of silicon, I'm assuming, to get all of those. Well, you have to go to the dense I/O, and then you have all of that. I don't know, maybe not. In the energy, I was under the impression from Robert Wang's presentation that if you don't in the short reach, you wouldn't need the FEX and all of the other compensations. So I thought the extremely short reach was actually lower, would be similar energy per bit.
I think still, if you want to push it to the for using serial link and do some kind of clock forwarding, and you're gonna still get something close to 1.2, 1.5 picojoules per bit. But
the other thing, though, as well, in design complexity, it's the same. It's just you're pushing it into your chiplet rather than being in the processor die.
No, the design complexity is actually pretty hard. That's why, for example, how many companies do you know that they have 112 gigabit per second serializer, and how many people they are right now advertising they have AIB? AIB is making it open source. All the code is available. Go and build it. Although it's not going to be as easy as it sounds.
But you still need to do the AIB on your chip. You need to turn it into transceivers on your chip. So the complexity is there. It's in one place or the other. It's just which chiplet is it on, is the argument. So the design complexity is identical.
And sorry, I'm not gonna agree with that, because the design complexity of the serializer PAM4 112 gig, it's way more complex to build the AIB with 1 gigabit per second.
But you wouldn't need PAM4 necessarily if you're only going over a couple of millimeters.
Then can you get the standard and low energy high bandwidth density if you're not going to the 112?
I must admit, I mean, that's an area that I don't know. I guess my only point is you still need to transceiverize the AIB either in the processor die or in the or inside your optical chiplet. So,
actually no, because from the CPU you're communicating with both sides is AIB, and that's actually happens in the 1 gig. You don't need to make it a serial link. It's a parallel link.
No, I know that. But when you're on your silicon, you have to turn the parallel bus into transceivers to convert into the optical.
Yeah, for example, in our case,
apologies, guys.
We are converting 25 gig, not 112. I mean,
that's okay. So you're going a lot slower. All right. So apologies. Okay, fair enough.
And basically, this is the structure that we pick. We are using EMIB from Intel for integration and AIB over it. I think if this is a slide, if someone wants to be interested, what is AIB? AIB is just a piece of silicon underneath inside the package between the two dies, and you get basically the 50 micrometer micro bump pitch connection to the die, and all silicon goes up. I think this is something that Intel wants. What we built was basically, this is architecture that we had. There's going to be a very large chip, main chip FPGA here, and these two small on the top and bottom that you can see is basically our Terafy chiplet, and this highlighted red one here is going to be basically the AIB link. And this is basically how the bump map between the FPGA and AIB is going to look like at the right, the micro bumps. This is our first demo. This is the Stratix 10 with the 2 Terafy IO chiplet here. Each of this chiplet again is going to give you each of them 80 wavelengths, if you want to look at it that way. 10 macro, each macro 8 lambdas. And you can see basically the comparing the size and area that it's taking and how much bandwidth you're gonna basically get out of it. Let me move forward. I promise Bobby to finish it soon. What do we have available right now to demo? We have basically 3 things. One is that we actually.
What is the bandwidth of each wavelength?
I have data for that, but we can go for 25 or 32 gigabit per second for now.
Thanks.
This is we have a basically single die package demo, which is only our own chiplet. I think if we want to talk about the business model and challenge of the chiplet, is basically you have to have this one as well to check yourself first. And then this is our basically platform for integration with the FPGA. The big chip that you see in the middle is basically 2 TB and 1 Stratix 10, which they are communicating to each other inside with AIB and over EMIB. But this is the basically demonstration of the MCP. And this is our basically the laser. I think the laser question, how we generate those 8 wavelengths and those other questions, you can see it that it's a separate chip. This is one of the demo that we did in Super Compute last year. This is basically the 8 lambda over 4 macro at 25 gig. We basically, for some challenges that we have, basically we were only able to couple 4 basically laser, 4 fiber optics to it. Nothing wrong with the chip, but it was basically how we wanted to demo. Then we need another of this set of the fiber optics, which wasn't available at that time. And we ran at 25 gigabit per lambda. This is basically the laser that you can see, 800 gigabit per second. We have 8 different lambda for each transmitter and receiver. And these are basically the internal eye that we collected. One of the challenge for having 8 lambda is stability. I think there's a lot of question over time, temperature change, how we make this system stable, because micro rings are generally not that much stable over the temperature. This is how basically we measured basically more than 15 hours. This is the initial chip package of heat up. You see that the heat values is actually changing, and then this is a lab temperature overnight. It's getting cool a little bit, and again, it's getting hot during the day. This is our basically bit error rate. We show basically in the 3 speed that we have. This speed is basically for 1 lambda. You can multiply this by 80 to get the whole bandwidth throughput. We can actually get easily to e to the power of -12 for all the 3 levels that we have. This is the statistical eye from our internal bit error rate. And this was another set of the simulation that we did this year with the multi-chip module. This is our own laser. It's actually going to the FPGA, to the laser goes to the package that we have with the FPGA. What we demo here is basically FPGA sends some signal through AIB, and AIB is going to pass it to us, to the Terafy by IR Labs basically, and we go through the fiber optic, we receive it back. Again, we pass it to the FPGA, we check if the data is correct or not. I think with all this demonstration, we are thinking that we can actually have kind of larger disaggregation in the architecture level. We can have more GPU and CPU communicating with each other with FPGA and ASIC through the fiber optics. I think as a roadmap, we still just demo 10 macros or 8 lambdas in NRZ. I think there are a chance for us to actually move to the 56 gig NRZ or 112 gig PAM4 in the optics, and then we can still increase the number of macros and number of lambdas that as we go, and we think at the end we can get to the 32 terabit per second per chip. And this is actually available for both organic substrate or silicon substrate as well, and parallel or serial interface. I think we are kind of open for it if customer wants a different basically link for the chiplet to main die. I think that was my conclusion. I think our evaluation kit is ready. If you have any further technical question, you can contact me or Vladimir at IR Labs or Shahab at irlabs.com. Or if you want, basically, if your company wants kind of evaluation kit, you can call Hugo at irlabs.com. Sorry, Bobby, I think I ran over time.
No worries. Any more questions for Shahab?
Just a quick technical question. Can this modulator change their lambdas on real time?
Real time, there is we do some adaptation because over temperature and basically process, those lambda is going to get changed. At the beginning, we adjust them to the lambda that we want, and then we track that locked lambda because the laser by itself is going to actually move a little bit. That's why we demonstrate the long hours of the tracking.
No, but I just wondering whether your last picture of the GPU and FPGA and CPU all together, whether it's possible to use those lambdas as a means of changing the routing structure.
If I understand your question correctly, basically on the fly you want to basically switch the lambda. And basically,
more. I mean, not in real time, but somehow changing the routings of structure.
I think that's what you do basically at the beginning of each initialization. We basically try to pick the lambda from the laser. Let me just this one. You see that it's all over the place from a range from 1260 to 1280. And to be honest with you, lasers are not pretty stable, and sometimes you're going to get it here, sometimes here. But at the beginning, we try to get locked to the most powerful lasers that we want, basically the 8 of them. But if over the time they change, we follow them. But if you have another application that you want to basically turn off and switch to another laser, for sure we can do that.
Okay, thank you.
But it needs adaptation. It's not going to be just as easy as it's just grab it.
Right, understand.
Any other question?
So Shahab, this is Lei. A quick question. So the eye diagram you're showing, those are optical or electrical?
As some of them are electrical, some of them are optics. I think, for example, this one is the one that you see mainly dot. They are basically electrical link that we are getting from our internal eye monitor. But the one that you see on the basically more continuous time, these are the optical eye diagram.
Oh, because I see. So you do have the on-chip eye monitor.
Of course we do, because we have 80 lanes, and it's impossible for us to basically have 80 optical oscilloscopes. It's too expensive.
Okay, excellent. So very interesting. I'll send you an email later on, because we're setting up a large carrier demonstration with some large company. So probably we can possibly put this optical link on top. Originally, we think to put the motion optical module. You know the motion, right? So yeah. I think this is very interesting. Okay.
Thank you.
Thank you.
If no more question, Bob, it's yours.
All right, thanks, man. Ravi, I was thinking we can do about a 15-minute prep today, and then redo this next week as well for the logo. Does that make sense?
Yeah, sure.
Okay. Hey, Shab, if you want to let Ravi present, yeah, thanks.
So hello everyone, this is Ravi Agarwal from Facebook. So this is a continuation of the discussion we had 2 weeks ago around when we had an open mic. And as a next step, what we decided is, as a community, we need to come up with the focus areas and which we would like to work in next 1 to 2 years. So with the help of Dharmesh, we came up with this 5 focus area and then, 4 focus area, and we asked community to vote so that we can collectively decide which one we want to work on. And as you can see, so far we have only 2 companies who have voted for these focus area. So I think this is something maybe we can have a discussion today first, whether what we have listed as focus area, are these the right focus area or should we modify? And then I think before the next meeting, I would still want us to go ahead and vote so that we can decide what we as a community want to focus in the next 1 year or so.
Can you make the display a little bit larger, please?
Sure.
Then,
is it better now?
Yeah, much better. Thank you.
I missed the voting link. Maybe you can send it out again.
Okay, I will send it later today. It is also part of the meeting minutes which Bapi sent out. It's just another tab in that, but I will send it later. So I think the question is, what is listed here as for like define what type of chiplet industry need for critical mass, define and develop chiplet testing strategy for known good die. And I think one of the thing which we discussed last open mic is like define a flow for simulation, building, integration, and ultimately delivery. So like a mock-up product. And then how should we think about yield? Because yield is very tricky, and then ultimately RMA is involved. But again, these are some initial suggestions. By no means these are final. So if the team thinks we need to add another focus area which is not captured here, please suggest.
What's the difference between 2 and 4?
What's the difference between 2 and 4? This is around only testing strategy. This is around once you have a chiplet, send it to another vendor, and if there is any fallout, then what kind of arrangement we will have between the company which is agreed upon. So this is more on the testing. This is actually finally yield, and then when something fall out during the assembly or integration, how do we come up with the business model between the two? And maybe there is an opportunity to combine 2 and 4. We can reword.
And 1 is also modularity, right? That's what you mean, I'm assuming, by what types of mod. Okay.
Yeah. And then for number 1, we actually thought maybe, if this is something we want to focus on, then maybe we can look into it. What type of chip industry need, and there are like some examples here, like whether it's a memory, FPGA, power and delivery, co-package, SRAM, or maybe we can say, rather than asking a very generic question, we can focus on 1 or 2 areas and then go and answer some of the other question like 2, 3, 4 for that particular segment.
And then we'll assess demand or something for each type, the kinds of designs and the market size, or take a guess at these things roughly.
Yeah. So we'll go deep dive.
Yeah, and Bapi, part of the motivation also is, I think a while back, ODSA community was debating or deliberating what should be the next POC, which we should be working on in ODSA. So some of these chiplets, depending on the need, timeline, and urgency, we could, use that data to inform us on what POC should the community work on.
Yep, it makes a lot of sense. In fact, I think honestly, there's a dependency that, unless you do 1, you really can't do 2, 3, or 4.
Exactly. But even to do 1, we need to decide as a community, like which one, because everybody have a different interest if you think about it.
So I have a very simple question for everyone on the call here. Broadly speaking, do we agree with that statement? Do you think defining 1 will subsequently define everything else? Even something as simple as do the type of chiplets have some kind of impact or effect on the way we do known good die discovery for those type of chiplets? Do we think that there is going to be a uniform mechanism, or do we feel that this mechanism could be very distinct depending on the type of chiplets? Any thoughts from anybody here?
Yeah, I was just going to say the footprint mechanical sort of the I/O of the interfaces. I think that is a minimum. So for example, I mean, for example, so that you could drop different formats down. And back to a couple of meetings ago when we were talking about test equipment on the transceivers, the fact that just bringing in old-fashioned test equipment is a problem. You'd almost want an oscilloscope or whatever, an analyzer on a chiplet, and maybe you could buy, either it's buried in every product, and that could be a key requirement. Every product has its own test capability, so it can verify itself against an IEEE spec. Or you would have some sort of ability to put a test chip down from an independent test manufacturer to talk to your chiplet And so things like that would mean getting standardized at the bump and mechanical level, and making everybody conform to that, so that you can mix and match chiplets. I think is a pretty fundamental piece of this.
Hey, so the other one thing I would add to the defining modularity is whether we also want to define a common infrastructure for the modularity. You know, do you want like a common controller, power supply, power delivery mechanisms, etc.? Defining what kind of common infrastructure you need for a modular design.
Yeah, actually, the power one's a big one, Bappy. That's a complex beast.
So I have a comment on Ravi's 4 items here. So I think maybe a slight modification or a subset of question number 1 will be will make it a little bit easier to think about. So if we break, let's say, these chiplets into 2 or 3 categories only. So let's say one of them is accelerators, the others are memories, and the third one are, let's say, sidebands or more standard footprint type of components. So the way I think about it is that there is a great potential for chiplets in the area of accelerators. So if we kind of like, you know, making it super generic and what type of chiplets, say what type of accelerator chiplets does the industry need, and then focus on the accelerators and their testing methodology, that would make it a lot easier for the new folks who are thinking about acceleration of different kind. So then the question becomes more interesting, that if you build a SIP and accelerators, for example, are swappable, right? So and then in the context of that, if we can define testing strategy and the yield, the problem gets a little bit contained, but it becomes quite a bit interesting. If you think about memory chiplets in high bandwidth memory, these questions have been answered in the context of that particular product, for example. So,
Joad, do you mind defining what do you mean by the accelerator? There are different types of definitions of accelerators, right?
One very simple one is, you know, you accelerate the inference calculations, for example, right? The inference pipeline. And there are obviously other kinds as well, but that's the hot one today. So if you think in the context of edge AI, or if you think in the context of data center AI, that's relevant, right?
But what does that mean? What are you recommending in terms of the focus area, Jawad? That is our group's charter, right? The accelerator part.
Right. So that's exactly my point, that if we focus on the charter of the accelerators, then if we think about, let's say that you were to build a pipeline, a chiplet that is an inference chiplet geared towards edge, right? So what would that look like? What kind of testing would be needed for it, and what kind of yield criteria could be set? I mean, one way is that we can think about generic problem of acceptable yields. The other is we can just put out a recommendation saying we recommend that the IO of these class of chiplets be designed like this? Will be kind of like a build up on top of bunch of wires, phi, so we can have the next level where we can define the testing strategy that takes into account yield considerations in the context of bunch of wires.
So Jawad, I think so. You are suggesting a subset of question one would be come up with a subgroup, whether it's accelerator, memory, and then let community decide which one we want to focus rather than. But I think the intent for poll 2 was exactly to answer that, and I can add accelerator too. Like right now, I don't have it here, and then ultimately we have to decide what we want to define as an industry for critical mass, whether it is accelerator, memory. I think we have to decide as a community.
Yes, the only thing is for a high bandwidth memory, all of these questions are already answered. So,
okay,
I think,
hey guys, I apologize. I need 5 minutes at the end to go over some critical opens. But I think what I'm hearing everyone say, if I translated, and we should pick this up next week because this is pretty cool, is focus on modularity, but focus on modularity for accelerators. So what components you need to enable to make accelerators easy to build, which kind of aligns straight on with what our charter is. So I think rather than modularity in general, I think the suggestion I hear is focus on modularity for accelerators. Is that about right, Jawad?
Yes, exactly.
Okay. And does that make sense to you, Ravi, in terms of the focus area?
Again, it does, but Bobby, only my question is, does everyone okay with making an accelerator as a focus area?
That leads to the natural next question. I think Ravi definitely needs he's taking the lead here. We need everybody to step up and vote or give Ravi some feedback, because I think then in the next meeting next week, we will go off and focus on one of these and go and say who wants to participate in being in the business work group, if I understand the sequencing right.
Yes, exactly.
Is that fair, DJ?
Yes, Bobby,
Okay.
and we definitely need everybody's input because obviously we all are coming at it from different perspective, and especially on line item number 1 and the poll 2, we would encourage folks to spend at least 30 minutes discussing internally within your company. It's quite possible that we might launch a POC in next 3 months, and you don't want to miss an opportunity here to influence a POC in the right direction. So it would be nice if everyone can chime in on areas where we should be looking at. Thank you.
Thanks. Hey, Ravi, would you mind doing me a favor and just adding the word modularity to choice number 1?
I will. Okay, sure, Ravi.
Thank you. Okay, so I need 3 minutes to go over some opens. One is this is the way our schedule's looking for the OCP workshop. I sent everybody so we have 2 panels right now. An end user panel, DJ, set aside an hour for an end user panel, assuming we can glue one together. The second is I've set aside an hour for management protocols for chiplets. I'm still not sure whether we can glue a panel together or maybe this will be covered in the management track. The third one is I'm thinking the memory discussion in chiplets is actually better off as a panel than a talk. So that's the third panel. Shahab wanted a panel on optics. I just don't have room for that, but if we do, we will we'll make room for it. And finally, somewhere I should have a 5 panel right here. So right now I have 3 panels. Maybe we can make it 4. And if you have, David from Seagate isn't here, but if you have people or other panels in mind, please tell me. We need to glue this together over the next few weeks. More importantly, what I want to do is record these panels in our meetings so that we have an audience Q&A for that. The second thing, my second big open is, you'll notice that in our agenda, I've completely removed testing and yield. That's because roughly a week before the before our ODSA workshop, I'm organizing, or I'm part of the committee organizing a workshop on testing for 3D and chiplets. So if you have, if you have any ideas, papers, please send them to that. I'll attach a separate call for papers for that link, for that workshop. So if you have any, so I'm moving all our testing stuff into that workshop. That's number 2, and there was a third open I wanted to cover. Excuse me, I wrote this down. Right. Anu, Lei, and Rita, I'm assuming you're still making reasonable progress on the open mic design.
Yes, we had a brainstorming session. You're making progress. When do you have that in mind? Just future,
roughly we have an opening on October 9th. October 9th, and if you think that, the one thing I'm sort of eyeing is if that looks really good, you can, even convert that to a panel at some point, and we'll rejig our schedule. So if you get something organized by October 9th, then we'll have room to decide whether to make it a panel discussion or not.
Yeah, but actually we talked about the possibility to do a panel. Yeah, so we can talk off.
Yeah. So if we get the open mic out of the way here, then we're in business. Then there's one more open I want to cover. Right. I was thinking that this is more a quick one. I was thinking that we should think about, there's a lot of information on the wiki. I feel like it isn't being used efficiently. So I set aside some time somewhere to think about how we want to organize the wiki and maybe highlight some information. Actually, I haven't set aside some time for that. And finally, one more thing I want to bring to your attention is we have a number of documents we're trying to release by the workshop. So we're going to have a session on the contribution agreements from Archana again at some point in about 3 weeks, because we've got the bow spec, we've got a pipe spec, we've probably got a link layer effort, all sorts of stuff in flight. And to release these as contributions or white papers, your organization will have to sign some releases. That is basically, and is Suresh still on? So one other important thing, we said the bow spec is making really good progress towards being tangible and having something concrete to put out. So we're actually beginning to get planning for a bow test chip. Suresh is going to do this. If you'd like to, or if you can, please help us plan this test chip and also contribute to it in some fashion. And at some point, we're going to pass the kitty around to get funding for a test chip. Our first step is to make the planning happen. And maybe Suresh, next week we can do 5 minutes about this in the lead up to the workshop.
Sure.
Those are my big opens. All right. Anybody else have anything? I've covered everything I needed to.
Just a memory one, what we were talking about slot in October, but you said leave that as an open.
Yes, because I wanted to see whether we can do a panel at the workshop.
I would just leave it until then.
No, not leave it until then. If we can find 3 or 4 people for a panel, then we would use one of these 4 dates to record it.
To record it. Oh, and that would be played back at the Tech Week. Is that what you're saying?
Exactly.
Okay. Right, that makes sense. Yeah, so I've succeeded, just on that, I've succeeded in getting a hold of Curtis Bowman. He's up for contributing on the Gen Z side. I've spoken to IBM on the OMI side. They're prepared to provide somebody, or maybe even I can help out. So that was I think that was the two actions on me to get interested parties. So
okay,
that's basically.
Yeah. So what we found last time was if we record the panel here, then there's a lot of lively Q&A, and it makes the whole panel sound better when we play it back.
Okay. Sounds good.
Okay. Anybody else have any opens? In that case, thank you all. Enjoy your weekend.
Thank you.
Ravi, thanks again.
Thank you.